All right, so if we take a look at this example, Euler's method, this is the type of question that you'll see. It says use Euler's method to approximate y of 0.3. Now y is just the function, and we're looking for the function value at x equals 0.3. Now we don't know the function. All we're given is the differential equation here. So we've got the expression of the derivative, okay? And we have an initial condition. So what we've done in the past is we have actually determined, right, what is the function value by integrating, using that initial condition and all that stuff, right? So we can come up with the equation of the original function, plug 0.3 in. But when that is not appropriate, we can use Euler's method to approximate. And all we need to remember is this down here. So let me read through the question. This is what we're looking for. Y evaluated at x equals 0.3 for the initial value problem given this. So here's the derivative, and that equals x plus y. Now remember, we could generate a slope field like this too, right? Remember we did slope fields? We could generate a slope field and know approximately what the function looks like. Euler's method is another way to show also what this function might look like, and given this initial condition. So again, I'll just rewrite this. dy over dx equals x plus y. Now this is going to be the value of this part right here, dy over dx, at the x and at whatever that y, initial y value is. So, okay, so initially we're starting at x equals 0, y equals 1, and I would strongly suggest you making a chart like this for these types of questions. Your x values, because we're going to have to do this a few times. Okay, so the initial value is 1 here and 0 here. Got that? Because that's the initial value of this problem.
Is this 0 for x and 0 for y?
Oh, I'm sorry. 0, 1. Thank you. Looking back and forth here. Yeah. It's the other way around. Good job. So 0, 1. My bad. Okay, so that's the initial value, right? Okay. So again, so we're going to try and get another point here, another y value, and this comes from the original y. This is like y naught, or our original one, or the one we're starting with. And we add to that, so the y value is 1, and we add to that what? What is this right here? Okay, so we got to find out what dy over dx is for this point, 0, 1. 0 plus 1 is 1. So this is 1. And then the change in x, we've arbitrarily set that change in x to 0.1. You see that? So we're going to find the next point over at a difference of the x values of 0.1. We're going to find out what that next y value is. Okay, so what does this equal when we add this up? It is 1.1. So guess what? That is the next y value, 1.1. Well, what is the next x value? Well, we're moving in increments of 0.1. So this is going to be 0.1. And then the next one, you could do this right away too, 0.2. And then the fourth point really is going to be 0.3. And that's actually what we're looking for. So this is what we're looking for right here. This is going to be the answer to our problem. The y value when x is 0.3. What's that? Okay, so no, we don't want to find this right away. Now, why is that? Because if we put in a change in x of 0.3, that's much bigger than 0.1, so we're going to be way off, right? So we're going to take this in littler chunks. Littler chunks. Now think about this. If we just go, here's our initial condition, that's a good question. And we go, hey, I'm going to go, hey, why did I do that? What did I just do? I don't know. I'm going to go 0.3, and I'm going to find out what that value is.
Musical practice will start right away.
The problem is that that's a big jump. What if we did it like this? Just go over 0.1, find out what this value is, then go over another 0.1, find out what this value is, go over another 0.1, you know what I mean? 1, 2, 3, I guess, whatever. Find out what this value is. So then there's going to be quite a difference here between what this value is and what this value is if we chunk it up a little bit more. Now, if we went 100th or more than a tenth, right, we would be going like this, and we would be having all of these little pieces, and maybe we'd be even more accurate, right? But then we're doing it 100 times or whatever, right? Lots of times. Does that make sense? So the more steps you have here, the closer the approximation will be. One step, not good. The question gives you this step, so that's good. That's what we're going to use. Okay, it's a great question. Why didn't we just go to point 3? We're going to do point 1. So let's go through this next row here together. So again, y value is 1.1. The derivative, remember, is defined as x plus y. And so that's going to be what? What is the x value here? 0.1, and then plus the y value is 1.1. So that's 1.2. You see that? It just comes from this plus this, because that's the description of the derivative there. And then, of course, the change in x is still 0.1. So now we have 1.1 plus 0.12, 1.22, 1.22. So at this next x value, this is 1.22. Okay, let's keep going here. So now we have 1.22 plus, this is going to be 1.42, because you're adding these two. Okay, times 0.1, and we're going to get 1.362 when you do that. And that is going to be our linear approximation using Euler's method. That's the approximation. So y of 0.3 in our calculations is going to be this. Okay. Now again, we could do the separable differential equation. We could separate it, take the integral of both sides, use the initial conditions, solve for that c, get a nice neat function, find out what the exact function is. We could plug 0.3 in there and get the exact value, but this is just a little different method to approximate that. And so in future classes and in future questions, you're going to have to do that. You're going to have to find the exact equation of f of x, plug this value in, and find out the difference here between the approximation and the actual value. But that's how you use Euler's method to approximate here in this question. Any questions?